Welcome back to part 2 of our study of the law of sines. In this video, we're going to look at the ambiguous case, which is the combination shown here, where you know two sides and the angle that's not in between them. We learned in the last video that triangles always follow this law of sines, which is a set of ratios between the angles and the sides. And so we can use that equation in this situation today. Now, the ambiguous case, again, is when you know two sides and the angle that's opposite one of those sides. And when you're given a situation like that, one of four different things can happen depending on how big side A is. First situation is maybe side A is simply too small. There might not be a triangle that can be formed. So that can happen. Because if you look here, this doesn't reach, right? I'm given this angle and it's just not big enough to form a triangle. Another situation could be that A is just the right size, and so one triangle is formed, and it would happen to be a right triangle. So that could be. It's also possible that A is just kind of this awkward in-between length where you get a triangle here, but you could also get a triangle over here. You get two different triangles, one that's obtuse, well, I guess they're both probably obtuse angles, but another possibility exists. A might be this kind of awkward in-between length where it actually is possible to form two different triangles. Let me show you. You get one triangle like this, but you could also get another triangle over here. And so in a situation like this, we're going to have to figure out both possible triangles that could be made. And then there's one other possibility. If A is significantly long, bigger than side B, for instance, then you could get one triangle here, but if you tried to make that second triangle, it just wouldn't work. It would be over here somewhere. So those are the four different possibilities, and they all depend on how big A is. Specifically, if A is less than B times the sine of A, then you can't form a triangle. If A is exactly equal to B times the sine of A, then you get your one right triangle that's formed. And if A is in between B times sine of A and B, that's when you have two possible triangles. And if A is really big, you'll have just one. So before we can look at some examples, we need to look a little bit more carefully at our inverse trig functions. When I taught you this the first time, I showed you that looking up an angle for a sine value you can do on a calculator by pressing something like second sine. I also showed you graphically that you can do that sort of thing by looking at a particular y value, say 0.8, and looking at this curve and figuring out at what angle that might happen. So graphically, it looks like it's about 54 degrees. If I were to type that into a calculator and press second sine of 0.8, it would give me 53.13 degrees. And that's great, but it's incomplete. There's another angle that gives us a sine value of 0.8. And that other angle we can only find if we consider the entire curve. If you notice, here is another spot where this curve reaches a height of 0.8, and that is close to 120 something degrees. Specifically, this 120 something degrees is the supplementary angle to the 53 that we found earlier. Supplementary means that you can find it by subtracting from 180. And in general, if you're going to look up an angle for a sine value, you really ought to think about maybe it's supplement 2. Here's a tool that we can use. If I were to type in 0.8 and do second sine of 0.8, the calculator is going to give me this angle here, the 53 that we found. You'll need to sometimes consider whether 180 minus 53 degrees is an angle worth thinking about. So now let's look at some actual examples. In this problem, we are told to solve for angle ABC, and we know that angle A is 122 degrees, side B is 12 units long, and side A is 18 units long. Now, you don't have to necessarily draw a picture to answer this question, but I'm going to do this for us. So let's suppose each of these line segments is about 4 units long. So let's make side B look like it's actually 12 units long. So yeah, that's pretty close to 12 units long. And I'm going to draw angle A as being 122 degrees. So if I'll rotate this around, 122 degrees is right about here. Now, side A has to be 18, and so I made this 4, 8, 12, 16, so 18 would be about that long. So somewhere around in there. So if I put this in here, let's see if this looks big enough to form 2 triangles or just one or what. So if I rotate this down, I think I'm only going to get 1 triangle here. A is too big in this case to form more than 1 triangle. So how do we find that triangle? Well, we can use the law of sines, and we can fill in the information that we know. We know angle A is 122 degrees. We know that side A is 18 units long. We know we don't know angle B. And we know side B is 12. We'll eventually get into angle C and side C, but for now, we have to look at this proportion and find angle B. So if we write an equation, we know that 12 times the sine of 122 is equal to 18 times the sine of B. To solve an equation like this, I want to get sine of B alone, and so I'm going to divide both sides by 18 a moment. And that equation, let's see, 12 times the sine of 122 divided by 18, that's equal to 0.565. So we know that sine of B is equal to 0.565. Now we need to think about what angles can give us a sine value of 0.565. So if we pull out a calculator and we type in second sine of 0.565, then the calculator is going to give us this 34.4 degrees. So that's about what this angle looks like. We also need to think about whether this angle, 145.6 degrees, could work for angle B. The 145.6 comes from taking 180 and subtracting 34.4. Now, 145.6 degrees certainly doesn't look like what's here, and it can't work in a triangle that also has an angle of 122 degrees, because 122 plus 145 is way more than the 180 degrees that a particular triangle could have. So in this particular triangle, there is only one triangle possible, and it has 34.4 degrees as angle B. To continue to solve this triangle, we'd have to figure out what side C, or angle C is, and then use that to find side C. For the sake of time, I'm not going to do all of that right now, but let me remind you, in order to find angle C, you would have to use the angle sum theorem. So 122 plus 34.4 plus C would equal 180, and you could do some subtraction to figure out what angle C is. Here's a second example. In this particular problem, angle A is told to us is 24 degrees. Side B, I drew earlier, is about 9 units long, and side A is 7 units long. And when we look at this particular triangle, which is drawn pretty close to scale, we see that side A is that awkward length where it forms two different triangles. So let's continue by pulling out the law of sines and filling in the information we know and don't know. We know that angle A is 24 degrees, and we were told side A was 7. We know that angle B, well, we don't know angle B yet, that's a variable, and we know side B is 9. And we don't know anything about angle C or side C yet, and so we'll have to wait on that until we figure out what angle B is. So once again, we can set up a proportion. We know that 9 times the sine of 24 is equal to 7 times the sine of B. And therefore, sine of B is equal to 9 sine of 24 divided by 7. And if we get out a calculator, that is approximately 0.5229. So sine of B is equal to 0.5229. So now I need to look up angle B. And to do that, I would type into my calculator second sine of 0.5229. And I would get an angle of 31.52 degrees. But that's not the only possible angle in this case. That's the smaller of the two angles. Let's see if we can make that triangle a moment. So that was the situation where angle B, which is this angle right here, is really small. So that's this triangle. However, you also need to think about the other possible angle. The other angle is 180 minus 31.52. And that is 180 minus 31.52 is about 148 degrees. And that would be the angle that we get when we look at this triangle. Notice angle B here is opposite side B. That's a really big 148 degree angle here. So at this point, we need to set up two different laws of sines. So I'm going to copy this over here, and we have two options. We have that option B, well, first option is that B is 31.52 degrees. And the second option is that B is 148.48 degrees. So to continue and figure out the remaining details for each of these triangles, we would have to use the angle sum theorem to find angle C. In this first triangle, 180 minus 24 minus 32 leaves behind 124 degrees for angle C. In the second triangle, 180 minus 148 minus 24 leaves behind only 8 degrees for angle C. And we can set up some proportions and find side C. One last example. In this particular triangle, we are told angle A is 47 degrees, side B is 8 units long, and side A is only 5 units long. And I've drawn this fairly close to scale, And so if we look at this, we can see that A is just not long enough to form a triangle. But what would happen if we just hadn't taken the time to draw a triangle and we just tried to solve it? We could put some numbers in here, right? We know angle A is 47 degrees, side A is 5 units long. We know angle B is, well, we don't know that, and we know side B is 8. And we could set up a proportion just like last time, right? That would be 8 times the sine of 47 has to equal 5 times the sine of B. And we should be able to divide both sides by 5 again. And we get that sine of B is equal to whatever 8 sine of 47 divided by 5 is. Type that in my calculator a moment. That gives us a 1.3 value. And so sine of B is equal to 1.306. And if we were to try to type this now into our calculator, second sine of 1.306, you'll get an error on your calculator. You'll get a domain error. So what if I use my tool here and typed in 1.306? What does it do? Oh, gives me errors too. And that's kind of the calculator's way of telling you that this is a scenario where there is no triangle possible. And so in this case, we'd be done. We could just write there's no triangle. So that's it for the ambiguous case and the law of sines. Tune back into the next video where we will talk about the law of cosines and solve some triangles that we wouldn't be able to with the law of sines alone.